Well, surprise, surprise, what we can do with bromine, we can also do with chlorine. We can chlorinate using Cl2 and iron 3 chloride as a catalyst. Let's just draw out a mechanism of that just so we're clear on it. We've got benzene, we've got chlorine as our two reactants. We have FeCl3 as a catalyst. Let's draw a ClCl. Let's draw an FeCl3. One of chlorine's lone pairs attacks the iron. We get chlorine half bonded to the other chlorine, half bonded to an iron, which can be attacked. Or another way to say that would be Cl plus and FeCl4 minus. Those are actually the same thing. The only difference is to what extent we've carried this reaction forward. Have I completely formed the iron-chlorine bond and broken the chlorine-chlorine bond, or are those still partly formed? Either one of these is perfectly acceptable in drawing a mechanism for using one of these iron compounds as a catalyst. Let's draw benzene. Going to attach to that carbon, so I'll put the H there. Double bond bouncing off a carbon, attacking the chlorine. Or, if you want to have it on the full structure there, attacking the chlorine and then breaking the Cl-Cl bond, which becomes the ClF bond. Right? We now have benzene where I have an H as well as a Cl. Two of the double bonds remain the same. I have a plus charge plus FeCl4 minus. The negative charge of that catalyst attacks the hydrogen. The CH electrons go back down into the ring, reestablishing aromaticity for the molecule. Product. Reformed the double bond. Now have substituted a chlorine instead of the hydrogen that I had there originally. The products I end up getting, we're not going to have FeCl4H, we're going to have FeCl3 plus HCl. We regenerated the catalyst. In order for something to be truly catalytic, it must be regenerated. For every 1 mole that's consumed, 1 mole needs to be regenerated. You could think of the bond from one of those, sort of the reverse of what's happening here, the bond between iron and one of those chlorines going out and attacking a hydrogen. So it releases an HCl from the complex right there. If I had asked you to include all resonance structures of the carbocation intermediate, we could do that pretty easily. I would have just brought the double bond over. Still drawing the H and the Cl on the sp3 carbon, but now bring the double bond over and do it again. So this time bring that double bond over like that. That's along with that one right there. So you only need to do that if you're asked to show all resonance structures. Let's write that, resonance structures of carbocation intermediate. There are 3 of them, right? Here's number 1, here's number 2, here's number 3. Right? So put that over there just so we're clear. Right? If all we're doing is drawing the mechanism of the reaction, that's pi electrons attacking the electrophile, then some sort of base present attacking that hydrogen and its electrons restoring the aromatic ring. A couple of other important reactions that can happen. If I have equimolar amounts of nitric acid and sulfuric acid, right? For instance, 1 mole of nitric acid to 1 mole of sulfuric acid. What happens, sulfuric acid is the stronger of the two acids. Here, let me draw its structure. HOS, 2 double bond O's on it, and OH. Since sulfuric acid is the stronger of those acids, one of the lone pairs on the OH oxygen in nitric acid will attack the H, one of the acidic hydrogens in sulfuric acid. So I now end up with protonated nitric acid. I have an OH2+, which is a good leaving group. So the O- of one of the nitro type oxygens, the O- will come down. That will kick off the H2O. So water will leave, and we now have our nitronium ion, which is NO2+. This is our very powerful electrophile. Has a full positive charge to it. If you look at its electrostatic potential map, the whole thing is bright blue. Okay? It's the nitrogen which is the site for a nucleophile to attack it. So benzene, one of its pi electrons, will attack the nitrogen. That will kick one of those pairs of electrons up onto an oxygen. So that forms a nitro group. NO2 attached to anything is called a nitro group. The water that left from nitric acid then can come in and remove that hydrogen, restoring the aromaticity. Really, anything that has lone pairs to it or is minus can be the base to remove that hydrogen. If I were to balance this, that sulfuric acid leaves a hydrogen sulfate, HSO4 minus ion, which could also be used to attack the proton, for instance. So if we have any water around, if it's an aqueous solution or if we've made water by dehydration of that nitric acid as it is, water is generally what it is, but in some cases where there's no water present, we have to find something to do it, like in this case. If I have SO3, sulfur trioxide, with sulfuric acid, a very similar thing happens. The O- will attack and become protonated by the sulfuric acid. That turns it into our very potent electrophile, which can be attacked by the benzene ring. It kicks an oxygen up. The base present here is most likely going to be HSO4 minus, because we can't do this with any water present. We have to have concentrated sulfuric acid with SO3. But the same mechanism. Aromatic ring attacks an electrophile. Some base or solvent or something removes that hydrogen on that same carbon that got attacked to reform the aromatic ring.